Hello. In this video, we're going to learn how to write our very first direct proofs. And all of the examples are going to be statements that we can prove only using the definitions of even and odd. So we're going to learn how to write very simple direct proofs. So what kind of things will we prove? Well, the first claim you see here is an implication, so it's an if-then statement, and the statement is if m and n are even, then m plus n is even. So one of my favorite sort of passages in our textbook is when the author, this is like on page 52 of the textbook, the author says that there's this distinction between correct logic and correct information. And sometimes you'll have to follow the logic of a statement, even though based on an incorrect assumption. And that ideally, your assumptions, like your information is going to be correct and your logic is going to be correct. But you should be able to follow the logic even if it's based on an incorrect assumption. Okay, so why am I saying that? Well, I'm saying that because proofs will depend on both, right? Assumptions and logic. And we have to make sure we're making the same baseline assumptions. And so the way we do that in mathematics is we make definitions. We assert them, right? And so the definition of even and odd that we're going to use in this course is here. So an integer m is even if there exists an integer a such that m is equal to 2a. An integer m is odd if there exists an integer b such that m is equal to 2b plus 1. So for example, so remember the first thing we do when we see an example, or if we see a definition is write down some examples. So I'm going to, using this pen, sort of make an example. So for example, 6 is an even number because, so how do I know it's even? Well, it's even because 6 is equal to 2 times 3, and 3 is an integer. So it satisfies the definition of an even number because there really does exist an integer a, and in this case the a is 3, such that 6 is equal to 2 times a. So often, I know you know what an even number is already, and students will say things like, well, a number is even if it's divisible by 2, or if 2 divides it evenly without remainder. So these things are all equivalent, but the definition that we're going to use in our proofs, the definition that's sort of good for proofs, is this one. And part of the reason it's good is that it tells you that something exists, this integer a, and it gives you an equation, and you can plug things into it and then move them around, okay? So let me show you how to prove this claim that if m and n are even, then m plus n is even, using this definition. Okay, so let's say, here's our claim. If m and n are integers and m and n are even, then m plus n is also even. Okay, so the way I think about direct proofs is I wrote a little poem, okay? So the direct proof poem goes like this. First, you write down what you want to show. Then you write down what you know. So I've already written down what I want to show, that's my claim. what I know is going to be my definition. And that's probably going to be one of the first things that I write in my proof. And then using that definition, I try to find a very small, in this case, computation that I'm going to do. And then I end the proof by writing down an interpretation of my computation that connects the computations, those manipulations, to the definition. Okay, the star of my proof is the logic. The computations are like the supporting evidence for my logic. It's like the stuff that you cite in a research paper, but the meat of the paper is your argument, your thesis statement, and how you put things together. And then you have to have this backup evidence. And the computations are only backup. They're not the stars. Okay. So when you're writing a proof, you want to state clearly what your claim is and where it starts and ends. And so I usually do something like this where I have claim written, and then I have my hypothesis and my conclusion. And then I want to tell you clearly when when all those assumptions are over and when my proof, where I think my proof starts. So I usually write an abbreviation, just PF for proof. So telling me where my logic is going to start. Okay. So here's how I'll start this proof. I've written down what I want to show. Now what I know is that M and N are both even. Okay, so I'll start maybe by writing, since M and N are even, well, then I know something about them. I can use this definition, okay? I know that there exists some integer such that M is equal to 2 times that integer. And there exists a different integer so that N is equal to 2 times that integer. And I have to use different letters for those 2 integers because they might not be the same thing. So I'll say, since M and N are even, comma, there exist K and L that are integers such that M equals 2K and N equals 2L. Okay, so here I've used the definition of even integers to get myself 2 equations, okay? The equation M equals 2K and the equation N equals 2L. So now I've done the first 2 lines of my poem, all right? And now I'm in my computation phase. Now, even though I'm going to do a computation, I still want my entire proof to be written in paragraph form. So every single part of my proof is going to be contained inside a sentence. Although sometimes I might sort of, if I have a long computation, kind of highlight it and put it out of line. And it's easier to read that way, okay? So since M and N are even, I've used my definition. And maybe I'll start the next line by saying observe. Oh, let me see. Do I have enough room for observe there? Maybe not. So I'll say observe that. Well, what do I want to know? My conclusion is about the quantity M plus N. So I'll say, well, observe that the quantity M plus N that I'm trying to conclude something about can be rewritten using those 2 equations in the line above. So that M is equal to 2K and that N is equal to 2L. Okay, and now I have to figure out one more computation to do so that I can use, reuse my definition and interpret this quantity M plus N as being an even number. So what I'm going to do here is I'm going to say, well, I'm going to factor. And so I get 2 times the quantity K plus L, okay, period. And I'm going to say, since we know K and L are integers, the quantity k plus L is an integer. So by definition, m plus n is equal to, it is even, maybe I'll just say that, is even. And I like to put 2 slashes at the end of my proof to show that I'm done. Okay, so what I have here is a proof that says, since m and n are even, by definition, essentially, so that's unwritten here but really assumed, there exists integers k and l such that m is 2k and n is 2l. Now I do my computation, observe that m plus n is equal to 2k plus 2l, one more line of algebra, and now I have a quantity that reads 2 times k plus l. Since k plus l is an integer, by definition, m plus n is even. So that last sentence, since, is the interpretation phase of my proof. Okay, let's do one more of these using the definition of odd number. Okay, so the claim is that if x and y are odd, then xy is odd. So this is going to be very similar to the last proof. So again, I've already written down what I want to show. The next part of my proof poem says, write down what I know. So it'll be similar to the last one. Since x and y are odd, there exist integers k and l such that x equals 2k plus 1 and y equals 2l plus 1. Again, here, the k and the l are kind of like dummy variables. They can be any letters that I want them to be. So they don't have to be like the B in the definition of odd. They don't have to be a letter B. They do have to be different letters because I'm not assuming that x is equal to y. So the k and l need to be different, okay? So I've written down what I want to show, and now I've written down what I know. I've used up what I know. Now I've got to do some kind of computation. Okay, I already used observe last time. This time I'm going to start with note that. Okay, so note that. So here I look, well, what am I trying to make a conclusion about? It's the quantity xy. So let's compute with that. Note that the quantity xy is equal to 2k plus 1 times 2l plus 1, based on my definition and the line above. Now here the computation might be a little longer than last time, so we'll have to do some algebra. And sometimes you have to have a little bit of algebraic perseverance. You have to just try something, try to carry it through patiently, and see at the end if there's something you can do. So let's see, I'm going to multiply these things out. So I should get 4kl plus 2k plus 2l plus 1. So now I look at that, and I've made it sort of uglier and longer, maybe. And I think, well, that's more complicated than the thing I started with. I want something of the form 2b plus 1. So I've got to find that. And when I look at it, I think, oh, look at this. There is a factor of 2 in each of those terms. So I'm going to factor it out. And so for my next step, I'm going to write 2 times 2kl plus k plus l plus 1. And I'm going to put a period there, right? Because what I see here is that this is an integer. So now I can say since 2kl plus k plus l is an integer, we see by definition xy is odd, okay? Because we really have written xy as 2 times some integer, and in this case the integer is a little complicated looking. It's that 2kl plus k plus l plus 1. All right, so that is just a couple examples of how to write a very simple direct proof. I'm going to keep these first direct proofs. We're just going to practice with the definition of even and odd in class on Monday, so that you can really focus on the logic, knowing that there are only 2 assumptions you can make, right? That things are even, numbers are even, or they're odd. And you can assume that, like, if you take 2 integers and add them together or multiply them together, you get another integers. So those are the only assumptions we have. And we're going to focus on the logic of how we put them together to write some simple direct proofs. All right, thank you.